This is my homemade calculator, and everything you see here is completely custom, from the schematics and PCB designs all the way down to the low-level software on the microcontroller. You can do the basic operations, including addition, subtraction, multiplication, and division. And since I find myself converting between dimensions and number-based systems, it's got a function for that too. Plus, the custom RGB backlighting looks kind of sick. This calculator is now a permanent addition to my workspace, and in this video, I'm gonna show you how it works. So the design of the calculator is broken down into 3 parts. The first is a switchboard that contains mechanical keyboard switches, as well as any components to implement the RGB LED backlighting. The second part of the design is a display board, which contains the microcontroller, liquid crystal display, and the power circuitry. The third part of the design is the enclosure, made from laser cut acrylic. And there's really a fourth part too, which is the code, and it's written in C. We'll step into each of these parts, first starting with the switchboard. The switchboard contains 31 mechanical keyboard switches. Not just any mechanical keyboard switches, but ones that are clicky. With 31 of these switches, we have enough to cover numbers, hexadecimal letters, operators, and a few function keys that will be used for conversions. Now the microcontroller needs to read these switches to detect key presses. We could run 31 connections to the PIC micro, but that's kind of overkill. And a common way to reduce the number of connections here is to lay out the switches in a matrix. All of the switch inputs are connected in columns, and all of the outputs are connected in rows. To detect a key press, the microcontroller has to scan the matrix. To do this, the PIC will power a single column at a time and read all of the rows sequentially. After the rows are read, the next column will be powered, and the process repeats indefinitely. When a switch is pressed, one of the rows will be seen as logic high. Now the software can detect which row is high, and it already knows which column is powered on. So using these 2 pieces of information, the software can determine what switch was pressed. So by implementing the switch matrix method, the number of connections to the microcontroller can be reduced from 31 down to just 12. That's big time. However, to implement the matrix properly, we need to add some blocking diodes to prevent ghosting. Ghosting is a hardware bug that makes the software think extra switches are being pressed, and here's how it works. Imagine 4 switches arranged in a matrix. The inputs are connected in columns, and the outputs are connected in rows. Also imagine that 3 of the switches are pressed, and if column 2 is powered on, row 1 will be logic high as expected. However, power is going to backfeed through 2 of the switches, making row 2 also logic high, even though that final switch is not pressed. So the software will register the last switch as being pressed, thus a bug in the system. This is called ghosting. To fix it, a series diode can be added to the output of every switch. Diodes only allow voltage and current in one direction, so this will prevent any backfeeding from happening. So to cut down on the number of connections to the microcontroller, we can put the switches in a matrix, but we have to add blocking diodes. It's a trade-off, and frankly an easy one to make. Each switch also has its own RGB LED, which gives the design a sick backlighting effect. Our little PIC microcontroller doesn't have enough juice to power these LEDs, right? I mean, each RGB LED has 3 LEDs, one for red, one green, and blue. Each one running at about 4 milliamps. So for 31 LEDs, that's what, 120 milliamps per color? No way our microcontroller can supply that. So each color will have its own MOSFET driven by PWM signals from the microcontroller. To finish up this block diagram, 3.3 volt power is supplied to all the components on this board through the connector. Ultimately, this power comes from the regulator on the display board, but more on that later. This is the block diagram for the switch circuit board. Pretty simple. Let's talk component selections. The specific switches I chose are Gatoron 3.0 blues. They have a nice pocket on them for RGB LEDs and a frosted dispersion lens to help diffuse the light from the LEDs. But the main reason why I chose the Gatoron 3.0 blues is because they come with a solid data sheet and a 3D model, both directly from the manufacturer. That makes a big difference when designing things from scratch. The switches need keycaps, and I found these ones on Amazon for a decent price. They're also backlight compatible for a clean LED look. Some of these keycaps found on the calculator design are 2U in size, U being a length descriptor when referring to keycap sizes. 1U being the smallest, 2U is used for things like the backspace key, and spacebars can be as large as 6U. My calculator has 4 2U keycaps, and all the remaining keycaps are just 1U. The 2U keycaps incorporate stabilizers in the design too, which help prevent the keycap from rocking if the switch is not pressed dead center. And the specific stabilizers used in this design are the Duroc Smoke 3.0s, and if anything, they just look sweet. Could probably get away with not using them if I wanted to. For the backlighting LEDs, I chose the T36K 3BGR series from Harvatech. They utilize a common anode configuration, run about 25 cents each, and are rear mounted, meaning they shine through cutouts on the circuit board. The benefit to this rear mount concept is that I'm not restricted to the size of the LED pocket on the switches. It's also super easy to hand solder. That being said, since these are discrete RGB LEDs, I need current limiting resistors and the MOSFETs to power them. Had I decided to use serial controlled LEDs like the popular WS12s, I could have saved money and simplified the PCB design. Alternatively, I could have used an LED driver IC as well, but maybe in the future. The exact MOSFET used to power the LEDs is the PIC32 from Panjit, and it was chosen because it's only 18 cents. It do be that way sometimes. It's got some decent specs though, such as a maximum drain current of 1.6 amps, which is more than enough. I mean, each LED color is only going to draw about 120 milliamps. The FET has a low gate capacitance of 98 picofarads too. Even though that's fairly low, the design incorporates a 100 ohm series resistor at the gate of each MOSFET to prevent this capacitance from drawing too much current from the microcontroller. Each MOSFET gate also has a 10 kilo ohm pull down resistor to prevent the gate from floating, because weird things happen with floating inputs. Finally, the FET also comes in a SOT23 package, which is super easy to hand solder. Now the PWM signals to these MOSFETs, as well as the switch signals, all need to go through a connector to get to the microcontroller on the display board. I decided to use a 30-pin flexible printed circuit connector, or FPC connector, from Molex, and let me tell you, I was terrified to use these things. I had a coworker telling me you'll be fine, and I kept saying, stop saying things to make me feel better. Turns out he was right. They're actually super easy to implement, and the 1mm pitch is pretty easy when it comes to hand soldering. These FPC connectors work with ribbon cables, and I love them because I can just purchase a cable, plug it in, and get a nice professional look. On the final design though, I did grossly overestimate the length that I needed, hence the ugly bend. Could find a new cable, but I spent too much money on this project as is. To actually design the switch circuit board PCB and schematic, I used an open source ECAD tool called KeyCAD. That's right people, it's pronounced KeyCAD. The schematic is 32 pages long and implements hierarchical sheets. The first page, also known as the root page, contains the 30-pin FPC connector, the MOSFETs for powering the LEDs, and the switch matrix arranged in hierarchical sheets. Side note, every time I hear the word hierarchical, I can't help but think of Halo 2.
I do not wish to keep the hierarchs waiting.
AKA the greatest video game of all time. Inside of each hierarchical sheet is a switch, series diode to prevent ghosting, a rear mount LED, and several current limiting resistors. Hierarchical labels link the hierarchical sheets back to the root page where the matrix connections are created. All the switch inputs are connected in columns, and all of the series diode outputs are connected in rows. Global labels then connect the output of the LED colors to their respective MOSFET for backlighting control. Also on the root page are some mounting holes, unnecessary silkscreen and solder mask layer graphics, and some do not populate capacitors in case of any power issues. Now the biggest benefit to using hierarchical sheets is with the PCB design. The calculator board contains 31 switches, 31 RGB LEDs, 93 resistors, and 31 blocking diodes. That's a lot of components, and placing and routing traces to all of these components would be awful. That being said, a free tool called Replicate Layout exists and can be downloaded from the package manager on KeyCAD. This tool allows me to copy the layout from one hierarchical sheet to all the others. So in other words, if I place all the components in the hierarchical sheet titled switch 1 where I want them on the PCB and then route traces to them, I can copy this exact same layout to the 30 remaining switches and LEDs on the other hierarchical sheets. This is a big time saver, and by grouping the outputs of the Replicate Layout tool, spacing the switches is a breeze. Mechanical keyboard switches require an exact spacing for a uniform layout and to make sure the keycaps fit together nicely. The best way I found to do this was to set the board origin to the bottom left mounting hole and then change the grid dimensions to 750 mils. To get the proper spacing, it's just a matter of clicking and dragging the grouped outputs from the Replicate Layout tool to the grid, and the spacing will be just perfect. After ordering the boards from JLPCB and getting reamed with tariffs, I started to solder everything together. Many of the component selections were based on the ability to hand solder the component. I mean, I could have used tiny resistors like 0402 tiny, and that would have saved some space and probably made PCB trace routing easier, but instead I opted for 0805 because I'm confident in hand soldering them. I also customized each of my footprints to help with hand soldering, such as the MOSFET footprint. I elongated the pad to make it super easy to get a soldering iron there. Probably went overboard. I mean, you could land a plane on some of these pads. All in all, it took about 3 hours for soldering the switchboard. I may just start having the PCB fabricator assemble my PCBs, but I got some good experience with soldering here. I also used water-soluble flux and solder, so to remove any residue left over on the board after soldering, it's just a simple matter of rinsing it under warm water and brushing it lightly with a toothbrush. The mechanical keyboard switches aren't going to be added until later because they have to actually snap into place on the faceplate, but more on that later once we start talking about the enclosure. So that's it for the switch circuit board. The next major part of the design is the display board, so let's go ahead and talk about that. The design of the display circuit board is much more straightforward. The heart and soul of it is a microcontroller. It's the command and control center for the entire operation. And the specific one used in this project is a PIC32, but more on component selections later. The PIC32 microcontroller talks to a liquid crystal display over a SPI bus. Now, the particular display used in the device does require a backlight since it's transmissive. It is nice to have a little control over the brightness of the LCD, so the display board incorporates a MOSFET driven by a PWM signal from the microcontroller. The drain of the MOSFET will drive the LCD backlight LEDs, very similar to how the LEDs are driven on the switchboard. To program the microcontroller, the design needs a programming jack that talks ICSP, or inter-circuit serial programming. ICSP is just a proprietary microchip communication protocol. It's effectively transparent to us. All that we really care about is that we need a few connections to the microcontroller. The PIC32 micro also needs connections to the switch circuit board we discussed earlier. Specifically, it needs 3 PWM connections for the RGB backlighting and 12 GPIO connections for the switch matrix. These will go through another 30-pin FPC connector, same one that was used on the switchboard. Finally, all these parts need power, so 3.3 volts will be supplied to the relevant devices from a linear regulator. The linear regulator itself will be powered from one of two sources, either a barrel jack or a USB connector. Both will be present, so a user has the option to use either one. And that really does it for the block diagram of the display board. Pretty straightforward. Let's get into some component selections. As I mentioned earlier, the microcontroller used in this calculator is a PIC32, and the specific one I'm using is the PIC32 MX530F128H. Probably overkill for the project. I mean, I could have used thousands of different microcontrollers, but I'm a microchip groupie. I'm familiar with their products, their tools, their ecosystem. Plus, I love their data sheets.
Nerd alert!
The liquid crystal display used here is the EA Dog M132 from Display Visions. It's got over 4,000 pixels arranged in a 132 by 32 grid, and an ST7565 LCD driver is embedded into the glass. The exact model of LCD used does require a backlight, and Display Visions, the manufacturer, has several options available. I opted for a simple white backlight to try and save some money. I could have saved a lot of money if I just used an LCD commonly seen in Arduino projects, but gross. I'll pay extra for a design that looks cool. For the programming jack, the design implements a solution from Tag Connect. The company makes a cable that connects directly to Microchip's programmer, and the other side of the cable mounts to a special footprint on the PCB. Pogo pins keep a solid connection to the footprint pads, and tiny plastic retention legs prevent the cable from coming loose during programming. The benefit to using this approach is that I don't have to put another connector on the PCB. All I need is that special footprint, and I'm good to go. I also don't have to create a special cable to connect the programmer to the board, which can be a hassle. The connections to the switchboard are accomplished with the same 30-pin FPC connector we saw earlier in the switchboard design. And 3.3 volt power is supplied to all relevant components on the display board from a regulator. The particular regulator the design uses is the AP2213 from Diodes Incorporated. It has a maximum input voltage of 20 volts, and it comes in an SOIC 8 package for easy hand soldering. Very easy and straightforward to implement, and it runs about 71 cents. The regulator itself is powered from one of two choices, either a barrel jack or a USB 2.0 connector. Barrel jacks get power from wall warts with the barrel connector, which are fairly ubiquitous, and I like to use barrel jacks in my projects because they are just so easy to implement, and I have several wall warts and barrel jacks left over from previous projects. A few notes on the schematic for this display board. The first is the use of blocking diodes at the input of the regulator to protect against reverse polarity. I've run into problems where the wall wart I'm using has a polarity opposite to what I'm expecting, and it fries the regulator. So these blocking diodes are going to prevent that. The next thing to note on the schematic is that the liquid crystal display requires a shit ton of capacitance to operate on a 3.3 volt power rail, so Don't be surprised when you see those in the schematic. The PCB design for the display board is pretty straightforward. Only two things really to note. First, I decided to use a 4-layer board to get some practice working with so many layers, and it really helped with routing signals to the 30-pin FPC connector. Second and last thing to note, don't place power and ground test points next to each other like I did here. It's too easy to short them together when getting a probe in there. I ordered the PCB blanks from JLPCB and then proceeded to hand solder everything together. The most difficult part of hand soldering here was the microcontroller. The 64-pin quad flat pack has a pitch of 0.5 millimeter, so it's super easy to bridge 2 pins together while soldering. To try and help prevent this, I added an extra pad at the end of each row of pins so that when I drag solder, any extra solder is deposited onto these extra pads instead of coagulating on the last couple of pins. It helped a little bit. Once the soldering was finished, the board was rinsed with tap water and brushed lightly. After letting the board dry, it was time to install both the switch circuit board and the display board onto the enclosure. But before we do that, let's talk about the enclosure a little bit first. I like my projects to have enclosures because it's practical and it looks good. But I like to show off the circuit boards in each project because that's where a lot of my time is spent in the design of these things. And there's no better way to do that than with clear-cut acrylic. So that's what this design implements. The big acrylic piece on top of the calculator is called the faceplate. It was designed in SolidWorks. I have the DIY license that's like $50 a year. To design it, a sketch was first created that contained the 31 cutouts for the mechanical keyboard switches. Mounting holes were also added to the sketch for the circuit boards. Once the cutouts were completed, the sketch was extruded to 1/16 inch to make it 3-dimensional. Now, the datasheet of the mechanical keyboard switches specifies a mounting plate thickness of 1.5 millimeters. And this is so that the little plastic retention tabs on each switch can snap into place. But the closest I could find to 1.5 millimeters was 1/16 inch, so that's what we're gonna use here, and it seems to work quite well. To get a decent viewing angle of the liquid crystal display from a seated position, the calculator faceplate needs to have a bit of a bend in it so that the LCD isn't just parallel with the desk it sits on. This is added in SolidWorks using the sheet metal tool, and after that, the faceplate design was done. But I also decided to add a bottom piece of acrylic just to prevent anything from shorting out the power rails. The design process there is almost exactly the same as the faceplate, except only 4 cutouts were needed to mount the switch circuit board, and no bend is required. Now, I don't have access to a laser cutter, but I worked with a company called Terrene out of Mukilteo. I worked with a company out of Washington to laser cut them for me. Super easy. All I had to do was send them the step files and they took care of the rest. I think it was like $100, so pretty reasonable. The acrylic came flat, so to add the bend to the faceplate, I just heated it over an air gun. And when the acrylic was hot enough, it was bent using a few pieces of wood and a cutting board from my ex-girlfriend. Thank you, Em. After letting the acrylic cool, the 31 mechanical keyboard switches were snapped into place and the switch circuit board added to the rear. Once the switch circuit board was added, I could start soldering all the switch contacts in place. And then I could add the mounting hardware that I found from McMaster-Carr. It's just 440 screws with several different sizes of standoffs. The display circuit board is also mounted to the faceplate using more 440 screws and more PCB standoffs. And then finally, a ribbon cable is added to connect the display board to the switch circuit board, and the hardware is done. But that's only half the battle. The real magic in this project is in the software, and it was a bear to create. So let's step into that for a little bit. The code for this project was written in C using Microchip's MPLAB IDE, and it's about 2,400 lines long. Combing through the code line by line, not really feasible. So instead, we'll just hit on some high-level concepts. After some initialization of various peripherals such as oscillators, timers, and GPIO, the software steps into an infinite while loop. And at the top of every loop is a function call to scan the switch matrix like what was described earlier in the video. If no key press is detected, a special function is called to update the RGB LED backlighting. This function takes a timestamp from a free-running counter and compares it to the timestamp from the previous update RGB LED function call. If enough time has passed between function calls, the red, green, and blue PWM duty cycles are updated, which will then change the color of the RGB backlighting beneath each switch. When the function exits, the infinite loop is run again, starting with the switch matrix scan. Now, if a switch press is detected during the matrix scan, the software will check if the key pressed was clear, backspace, or enter. If none of these, then the key pressed is either a digit, operand, or function key. Whichever it was, it's going to be added to an input expression buffer that tracks all the key presses from a user. user. This same input expression buffer is then used to update a block of memory in the PIC32 that exactly resembles the LCD pixel layout. The code refers to this block of memory as video RAM. The video RAM is then sent to the LCD via the SPI bus, and the RGB backlighting is updated before the loop is run again. If a user presses the enter key, things get complicated pretty quickly. At a very high level, the input buffer is first tokenized, meaning the array of input key presses that's been logged up to that point is translated into meaningful information that the PIC micro can work with. The output from this is a bunch of tokens that are then evaluated. The result is then parsed, and the output expression buffer is updated before the video RAM is refreshed. As before, the video RAM is sent to the LCD, and the RGB backlighting is updated before the loop is run again. If the backspace key is pressed, the most recent key press in the input buffer is erased, and then same old from there. If the clear key is pressed, both the input and expression buffers are zeroed out, and the cycle continues. This flowchart is very high level, but I did want to touch on the font in a little more detail, and from here on out, I'm going to refer to a single character on the display as a glyph. The glyphs in this project are custom and were created using GIMP, a free open source raster image editor. Each glyph is 16 pixels tall and 12 pixels wide, resulting in characters that are readable from a seated position. After creating the glyph bitmap in GIMP, the file was rotated and exported as a PNG. An online tool called Marlin Bitmap Converter was then used to translate the PNG to a binary array in C. I don't like binary arrays, so I used ChatGPT to convert them to hexadecimal and add some cool comments for visualization. Not strictly necessary, but I like it. This process was repeated for every possible character to be displayed on the LCD, and the resulting bitmaps stored in their own C source file, ultimately winding up in the PIC32 RAM and consuming about 800 bytes. When the full code is compiled, MPLab is showing that the software consumes about 24 kilobytes of memory and 2 kilobytes of RAM, or 18 and 12% respectively. That's pretty solid. So with the code finished, we can now just flash the software. It's a simple matter of connecting the tag connect cable to the display board and flashing it, and everything works well. So yeah, that's the whole design in a nutshell. I hope you liked it, and I'd be very curious to hear your thoughts on what I could do differently or what I could do better, right? I mean, engineers are never satisfied with their work. I have a whole list of things that I could improve on, but I'm curious to hear what you have to say, so drop that down in the comments below. So with that, thanks for watching, and if you want to see more, you know what to do.